Okay, let's talk Module 4. Um, so Module 4, isomerism, nomenclature, two big words to make you sound smart once you know what they are. Um, but they're really not that complicated. Um, the first thing I did in the unit was introduce saturation versus unsaturation, because it can be a useful tool to help you figure out how a chemical formula relates to the structure of a molecule. So when you say something is saturated in general, what does that mean? Oh, so you may have heard this in the context of fats. Actually, saturated fats. These are the unhealthy fats, actually, or less healthy fats. Um, unsaturated fats are actually more healthy. No, it's saturated are the bad ones. Unsaturated are the better ones. And I spelled it wrong, so I'm gonna fix that because that's gonna bother me. Unsaturated. Um, yeah. So in the context of fats, you may have heard this, but in general, like this word saturated comes up in different contexts from time to time. Um, in a business class, you might talk about how saturated a given market is. Um, when you're washing a car, you might talk about how saturated a sponge is. What does it mean to say something saturated? We have any idea? All right, a saturated sponge would be really wet. In business, a saturated market would be one where everyone already has the thing you're trying to sell. Okay, um, so saturated means that it holds as much as it possibly can. And unsaturated means has room to hold more. So, in to go with the business analogy, if you say the market is already saturated, that means you're going to have a hard time selling the thing you want to sell because everyone already has one. Um, Whereas if it's an unsaturated market, that means you can find people who don't have it to sell it to already. Um, but in chemistry, what we mean when we talk about saturated versus unsaturated, we're talking about hydrogens. So how many hydrogen atoms the molecule holds. So a saturated molecule will hold as many hydrogens as possible. So for example, some saturated molecules would be like C2H6. There's no way that two carbons can hold any more than six hydrogens. Another example would be methanol, CH4O. There's no way for one carbon and one oxygen to hold any more than four hydrogens. Some examples of unsaturated molecules would be things like C2H4. Or formaldehyde, CH2O. So when we talk about fats being saturated or unsaturated, a saturated fat has as many hydrogens as it possibly can hold. Unsaturated fats are going to have some room for more hydrogens. What is it that I did to take away hydrogens? I added a double bond. Yeah. So in unsaturated fats, there are some double bonds. In saturated fats, it's all single bonds. And we can talk at a different point about why that makes saturated fats versus unsaturated fat, why that makes different fats more healthy or less healthy. All right, so it turns out that there's this correlation between number of hydrogens on the atom and double bonds. And we can calculate what we call the unsaturation number. So this is basically a bookkeeping method to relate the chemical formula to the molecular structure. Some of you would have derived this formula when you worked through the packet. Some of you might have looked up this formula. But the unsaturation number for a molecule is going to be 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of X here stands for halogen. So X is fluorine, chlorine, bromine, or iodine. All that divided by 2. So it's this mathematical formula we can apply to tell us what the unsaturation number is. Now, in terms of the structure, U tells us how many rings and or pi bonds there are on a molecule. And pi bonds you'll learn more about in Module 5 if you haven't gotten there yet. But a pi bond is the second bond of a double bond or the second and third bonds of a triple bond. So every double bond adds 1 to your unsaturation number. Every triple bond adds 2 to the unsaturation number. So when you look at a structure, you should be able to relatively quickly determine what its unsaturation number is, because you're just counting these extra bonds and the rings in the molecule. So just to give an example, or to give a couple of examples, if we look at these molecules up here, first one, what's the unsaturation number? 1, because it has one ring. Second one, 2, it has one ring plus one pi bond. This third molecule, 0. That's a completely saturated molecule. This one here, 1, 2, 3, because there's 3 pi bonds. This one here, well, it's got 2 rings, plus it's got these 2 pi bonds. So this one's going to be 4. And that last one, 1. It's got the 1 pi bond. All right, so the next thing we talked about after introducing unsaturation number was isomers. So how do I define isomers? Same chemical formula, different structure, meaning they're different arrangements of the same atoms. So for example, for C3H6, I can apply my unsaturation formula to this. It's going to be 2 times the number of carbons, which is 3, minus, plus 2, So going back to the formula, 2 times carbon plus 2. I don't have any nitrogens. I don't have any halogens, any X's. So I just have to subtract the number of hydrogens. So it would be 2 times 3 plus 2 minus 6 divided by 2, which gives me an unsaturation number of 1. Well, there are 2 different ways I could have an unsaturation number of 1. Bless you. What's one way I could have an unsaturation number of 1? A double bond. What's another way I could have an unsaturation number of 1? A ring. So those would be 2 isomers with the formula C3H6. So notice how we just used the unsaturation number to help us draw the isomers. As we said, if it's an unsaturation number of 1, how many different ways can I do that? So the unsaturation number can be a tool for us to come up with different isomers. Of course, the formula can be more complicated and we can still make it work. So for example, if I say C4H9NO2. Go ahead and find the unsaturation number. So the question is, does O count as X? No, O, it turns out, oxygen doesn't factor in. And this O here means oxygen. So oxygen's not part of our formula. So if you're going to draw different isomers with the same formula, once you've calculated the unsaturation number, you want to make sure that nitrogen makes, how many bonds does it like to make? 3. How many bonds does oxygen like to make? So make sure that each nitrogen makes 3 bonds. Make sure that oxygen makes 2 bonds. Make sure your structure has the correct unsaturation number. And if you follow those, then whatever you draw should be a valid structure. If your nitrogen is making, say, 1 bond to carbon, how do you fill in the other 2 bonds? With hydrogen. So on nitrogen and oxygen, you want to fill in H's as necessary. So go ahead, draw a few. And you can draw them as skeletal structures and not have to bother drawing out all the hydrogens, except for the ones on nitrogen and oxygen. The beauty of unsaturation number is you shouldn't have to count your hydrogens. See what you can come up with. I'll bet there's hundreds. You should be drawing structures with one pi bond or one ring, because the unsaturation number here is 1. So if you find yourself drawing more than one pi bond or more than one ring, remember only 2 bonds for oxygen. So if oxygen has a double bond, there's no hydrogens on it. One piece of advice is don't just string the nitrogen and the oxygens together. Integrate them into the structure. One thing I've seen in a lot of structures is people will just kind of throw the nitrogen and the oxygens in there like as NO2 without really specifying how they're bonded. Do you have a question? All right, I gathered up some of the answers, some of the structures that were drawn, and just want to go through and see which ones make sense. how we might make some fixes on some of them. All right. First one up here. Let's up on the left here. Unsaturation number. Does it have 1 degree of unsaturation? Yes. It's got a ring. It has 1, 2, 3, 4 carbons. That's correct. It's got a nitrogen and 2 oxygens. That's correct. So this structure should be fine. I might change it slightly by just being more explicit about what this NOH means. And just showing a bond here to go to the OH. But that's a valid structure. We'll see that, having nitrogen and oxygen bonded in this way, probably not something we're going to see at any point in the course. It's not one of our common functional groups, but valid structure for an isomer. Second one, to the right there. Does it have 1 degree of unsaturation? Yes, it's got a double bond. It has 1, 2, 3, 4 carbons. It's got a nitrogen. It's got 2 oxygens. So, is it all good? Is there one thing we should fix? Yes, what is that? Nitrogen has 4 bonds here. So, I'm going to cross out the hydrogen there. So that nitrogen only has 3 bonds. And then it should work. Up here to the upper right, 1 degree of unsaturation, yes. 1, 2, 3, 4 carbons, yes. 1 nitrogen, 2 oxygens. Any way to fix that structure? Or anything wrong with it? Nope. This one's good. This one was good. This one, now that we fixed it, is good. All right, down here to the left, I've got 1, 2, 3, 4 carbons. I've got a nitrogen, 2 oxygens, 1 degree of unsaturation. This one works. This next one here with the ring, I like that. 1, 2, 3, 4. Nitrogen, 2 oxygens. That works. This next one over here, what do we need to fix about this one? Needs another carbon. Right now it only has 1, 2, 3 carbons. So I can throw another carbon on somewhere, wherever I want. Maybe I'll add a methyl group here. All right. What else needs fixing? I have 2 oxygens here with 1 bond each. So I need to put hydrogens on them to give them each a second bond. Anything else? Nitrogen. Nitrogen has 2 bonds right now, so I should put a hydrogen on it to give it 3. So now that one's good. This one down here, I've got 1, 2, 3, 4 carbons. So that checks out. I've got a nitrogen and 2 oxygens. Is it clear how the nitrogen and the oxygen are bonded? Not really. We've seen NO in a couple of these other structures. Like right up here we see NO, right up here we see NO. If you just have NO on the end of your molecule, what kind of bond do they have? A double bond. So if they had a double bond, that would give me 2 degrees of unsaturation, so that wouldn't work. So one thing I could do is add a hydrogen to the nitrogen, add a hydrogen to the oxygen. Then they'd have a single bond to each other, and that could work. This one down here has 1, 2, 3, 4 bonds, 1 degree of unsaturation, has the two hydrogens, the two oxygens and the one nitrogen, so that one's good. And this one here, 1, 2, 3, 4 carbons, that's good. One ring, that's good. Nitrogen, two oxygens, anything I need to fix? The nitrogen only has one bond right now, so I'm going to have to put two hydrogens on it. All right, so there we came up with 9 different isomers. There are probably hundreds, if not thousands, of correct answers to that. Some of them more likely than others. Of the molecules we have on the drawn on the board, most of them are actually unlikely to be particularly stable. The ones that have the functional groups that are on your list are probably the most likely ones. So maybe the one down here. So I can see an amine, a ketone, an alcohol. Those are all kind of standard functional groups. That molecule probably exists in a stable, it's probably a stable molecule. A lot of the others probably not, but that's okay. Any questions about coming up with isomers? All right. So then we had a bunch of rules for how we name things. My whole purpose in introducing naming is not because I think that naming molecules is all that important. I don't. But what the naming rules do is they force you to think about molecules in a systematic way. And that can help you distinguish between two molecules that look similar but might be different or might be the same molecule. So the whole reason that we're doing any naming is just to get you to think about molecules systematically. So when you name molecules, the key is first you find the longest chain. Once you find the longest chain, then you're going to identify all the what we call substituents. Those are just the things that branch off of the chain. And then you need to number your chain so that you can tell which carbon atom each substituent is branching from. And here it's really important that you number in the direction that gives you the lowest number for the first substituent. Yeah, number in the direction that gives the lowest number to the first substituent. I'm not going to go through and list all the how many carbons goes with what root. Hopefully you looked up a list of how many carbons go with what root. So like 1 carbon goes with the root meth and 2 carbons goes with eth. you can look up these lists. I don't know how they came about. Actually, I don't know who originally decided that these would be good indicators of how many carbons were in something. But you do need to look those up and use a list because everything gets named based on how many carbons are in it. So let's do an example. Uh-oh. Looks like the battery in my pen is dying. Let's see if I got it back up. Oh, looks like my backup's dead. Oh, got it. All right. So here's my molecule. If I want to name this molecule, first I need to find the longest chain. So go ahead, find the longest chain that you can find in that molecule. And don't be fooled, it's not always going to be just simple follow the chain that I drew first. So how long is the longest chain in this? 9. Longest chain I can trace from up here. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. That tells me my name will end in nonane. Because non stands for 9. Now I have the question of how to number it. I've got to identify my substituents, I guess, first. So I see a substituent right here. I see a substituent right here. And I see another substituent down here. My two substituents that I circled in blue, how many carbons does each of those have? 1 carbon. So those 1 carbon is meth. We'll call those methyl substituents. The green one has how many carbons? Oh, I wrote it up there, so I gave it away. So we're going to call that an ethyl group. So I've found my chain. I've identified my substituents. Last thing to do is going to be to number. And I can number my chain in 2 different directions. I could go 1, 2, 3, 4, 5, 6, 7, 8, 9. Those purple numbers. Or I could go with these orange numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need to choose the direction that gives me the lowest number for the first substituent. Is that going to be purple or orange? Orange. If I go with the orange numbers, the first substituent's on carbon 2. With the purple numbers, the first substituent would be on carbon 3. Yep. With the orange numbers, the first substituent is on number 2. With the purple numbers, the first substituent is on carbon 3. So, 2 is less than 3. So I go with the orange numbers. So in the end, now I'm going to name it by listing my substituents and then putting nonane at the end. So I know the end of the name is nonane. I have an ethyl group and 2 methyl groups. I'm going to put the 2 methyl groups together and call it dimethyl. And they're on carbons 2 and 7. So I would say 2, 7 dimethyl nonane. Then I need to say that there's an ethyl group on carbon 4. So I would say 4-ethyl 2,7 dimethyl nonane. I don't really care if you follow this convention, but the convention is to list the substituents in alphabetical order. So that's why I chose to do ethyl before methyl. I don't think that's an important rule for us. I also don't think it's important whether you get the dashes and the commas right. I just care that you can identify the chain, name the substituents, and number correctly. And if you can do that, great. Question? Oh, so the question is, for alphabetizing, why do I ignore the di in dimethyl? That's another rule. And, I don't really care that you know the alphabetizing rules. So whichever order you would put these in would be fine with me. All right, so that's how you name alkanes, and you have a bunch of examples in the skill builder. I also wanted to give you at least one functional group that you have to name. It's only slightly more complicated. So if you're going to name an alcohol, what you would do is choose the longest chain that contains the alcohol. So you're going to choose the longest chain that has the OH coming off of it. You're going to identify and name all the substituents. And then when you number, the difference is you want to make sure that the alcohol group gets the lowest number. And the last thing is, on the end of your name, you put OL. So since we're just about out of time, just to give a quick example. If I had this molecule here, I'd identify my chain as 1, 2, 3, 4 carbons. So 1, 2, 3, 4. I'd number it from right to left to put the lowest number on the carbon with the OH. And this would be 3-methyl 1-butanol 3 tells me I have a methyl group on carbon 3. The 1 tells me that the OH comes off of carbon 1. All right. Thanks, guys.